All right. Hi, everybody. Welcome back to office hours. Hope everybody can hear me okay. Okay, so let's just jump right in. So today we're going to do these warm-up questions. So you guys do know 3 reactions so far. Your 3 reactions are A, B, and C, and actually in the order that you learned them. So you should know reactions A, B, and C already. So let's see if you guys were right. So the first thing we see is a hydrohalogenation reaction with this pi bond. So remember, pi bond is our nucleophile, the hydrogen is our electrophile, and we talked about reasons for that. And remember that bond in between that hydrogen and that halide, that electron density is going to be retained by the bromine because it's more electronegative than the hydrogen. Okay, so the result is some sort of intermediate structure. Okay, and we know it follows Markovnikov's rule where hydrogen is going to add to the less substituted side of the alkene, and that forms a carbocation on the more substituted side of the alkene. But always check for potential rearrangements. So right now we have a secondary carbocation. So we see at the adjacent position to the left, we have this source of hydride that we could transfer over to form a tertiary benzylic, carbocation. And this pH equals benzene. The rest of the molecule are. So if you see pH, that's just an abbreviation for benzene ring. Okay. So then the result of this mechanistic step, this hydride shift, would result in, a tertiary benzylic carbocation, and then free bromide, which is hanging out, is going to attack at that position. So I would expect, maybe a mixture of that specific stereoisomer and as well as the other. All right, and that's it. Okay, so for B, we're going to do acid catalyzed hydration. So remember, whenever we have more than one reagent in solution, we have to, think to ourselves, what is the product of just these reagents mixing together? Okay, so water plus acid isn't water or just acid, it's actually hydronium. So that would basically be, this main reagent. So just the protonated version of water, excuse me. So what happens is that this pi bond is going to do that same mechanistic step, grab a proton, which is our electrophile, and then that oxygen retains that electron density. So then the result is, another carbocation intermediate, where our carbocation is on the tertiary position, putting our hydrogen on the secondary position, and then we're left with an isopropyl group on a dash. Okay, so a very, very good hint for you guys is whenever you see stereochemistry of a group, and we're not necessarily doing any chemistry at that position, meaning we're not reacting at that position, you want to leave the stereochemistry the way that it is. So if I see, maybe a dash isopropyl group, I'm going to leave it a dash isopropyl group and never play with that stereo center because I'm not doing any sort of chemistry there. Okay, so we should just leave that. So the result from that step is going to be, this carbocation intermediate and then water again. So then water is going to act as my nucleophile, attack at that electron deficiency, and I'm going to be left with, H, and this is positive. So we have one more mechanistic step, and that's going to be assuming we have excess water in solution, and that's true because, catalyst indicates that it's a small amount of, or small stoichiometric quantity. So then this, water molecule can again act as a nucleophile, deprotonate one of those protons, and then, officially synthesize some sort of alcohol. So remember, there is no a sigma plane of symmetry, but what we do have here is a mixture of geometric stereoisomers. So we would have to consider, the trans arrangement where the hydroxyl group or the alcohol group is, on the same face as that high priority isopropyl group. So this would be the, cis conformer. Okay, so that would be cis. And then we'd also have to think about the trans one. Okay, so trans one would be, all right, and those would be my 2 structures. This would be trans. Okay. All right, that's B. And then for C, it's the same exact thing that we saw before, but instead of there being a hydrogen that also comes for the ride, it's going to be this, ethyl group that comes for the ride. So see how we have a hydrogen here? Instead, it's going to be an ethyl group. Okay, so what's going to happen is we have this protonated alcohol. So I'm just going to now skip steps because I think you guys have seen the mechanism enough times. This nucleophilic pi bond is going again, grab a proton. That oxygen retains the electron density. We're left with, this secondary carbocation. Yes, I see two alkyl groups next door, so I'm going to do an alkyl shift instead of a hydride shift. So then that results in that structure, and then your alcohol group is going to come and attack there. So I'm going to go right to the products, and the product of that is going to be okay. And there are no stereoisomers, more stereoisomers than the structure, because this is an achiral center because it's two methyl groups. Okay, so that was just a review of our 3 reactions at this point. Nothing new. Remember, keep in mind, anytime that you go through these carbocation intermediates, we always have to check for some sort of hydride, alkyl, or ring expansion shift. Okay, so that's it for A, B, and C. Does anybody have questions on those? All right, so I'm going to go on to 2. So this is just, again, reviewing, carbocation stability. So, we have these 4 structures, and we want to rank them in terms of increasing stability. So what do we not know, or what's implicitly depicted here? And that's going to be these lone pairs on the nitrogen atoms, okay? But specifically, there are no lone pairs on this ammonium kind of structure, because when you have 4 bonds to nitrogen, you're using all of the lone pairs that would have been on nitrogen. So there is actually no lone pairs here. That's the key finding. The difference between the amine group, amino, NH2, and the ammonium, functional groups. Those are 2 differences. One has lone pairs, one doesn't. Okay, so knowing that was half the battle, because now that lone pair is going to be, capable of donating some of its electron density to fix that deficiency. So, let's look at this first structure. We see we have this lone pair, definitely can resonate to the left and definitely can stabilize that structure. However, it's also, oh, can you guys see everything? Okay. Okay, so that lone pair can resonate to the left and stabilize that deficiency, but it also is equally likely resonate to the right and, resonate with this carbonyl. So, yeah, it can donate and fix that deficiency, but it's also slightly tied up in resonance with this carbonyl. So it doesn't do, as great of a stabilizing effect as this one would, because this, structure has complete, donation to that deficiency, and it's not tied up with any other, structure. So, definitely I would say this would be my most stable structure. And then, this one would be my next most stable structure, because they both have resonance. Okay, and then between, this ammonium group and then this just plain secondary, what is the difference? Well, this ammonium group, since it doesn't have lone pairs, is really just an inductive group, okay? So that makes this carbocation even more electropositive, so that's even more unstable. So that would leave this secondary one as a intermediate in between, this slightly stabilized one via resonance and this completely destabilized one via induction. And that's kind of how I would rationalize those. All right, do we have any questions? I think we have one. Induction. Yeah, you could also rationalize that too, fair, that works. So for structure A, yeah, you can either use the slight resonance example or you can use the inductive example. You can definitely argue that that carbonyl functional group within the amide is slightly inductive, so it destabilizes just a little bit, even though that lone pair also stabilizes just a little bit. 4 is the most stable because we have complete resonance that can donate and fix that electron deficiency. But the reason why this one was better than this one was because in this structure there was also some resonance with these lone pairs in this carbonyl. So you can't say at any given point that all the lone pairs are going to fix this deficiency, because maybe they're slightly fixing this deficiency. Remember, there is an electropositive center at that carbon of the carbonyl. So it's fixing that deficiency and not that one. And that's kind of why we have that. Okay. Hopefully that makes some sense. And then we're just going to jump into some more reactions. Okay, so let's go on to page, I wanted to do this last class, but we didn't get to that reaction. So let's go to page 62. And we're going to do, this reaction coordinate diagram. So this has been tested a couple times in the past semesters that I've been, TAing Orgo 1 and 2. And it seems daunting because nobody has, seen these reaction coordinate diagrams in a while. But the best thing I could tell you to do for these is draw out the full mechanism and then look at the questions after. Okay, so I see some sort of reaction, just draw that reaction, draw the products of that reaction, and then answer your questions later, and maybe it's going to make more sense. So because I said that, let's do that. So I'm going to transfer this question over. So it looks like this. Okay, and it looks like I'm reacting with CH3, CH2OH is just ethanol, so it's 2 carbons and the OH, and then HCl catalyst. Okay, and I'm gonna move this book out of the way. Okay, so again, I hope you guys are doing this as we're working along. So, these two reagents react together, this alcohol and this acid, to form the protonated acid, the protonated alcohol, I should say. So that would be, this structure. Okay, and these steps already. This pi bond is going to grab that proton, and then that oxygen retains the electron density. So the result is this carbocation intermediate, and this should have big bells in your head going off to indicate that, this is the telltale sign of a ring expansion when we have that, double bond adjacent outside of the ring of a 4 or 5 membered ring. So we can expect, some sort of break here and then, restructuring of this, ring to form a 6-membered ring. So in doing so, we have a rearrangement, and we can, maybe number the parties of the ring. So we have 1, 2, 3, 4, 5, and 6. Okay, so we have a 6-membered ring now. Okay, so we can call that 1, 2, 3, 4, 5, and 6. Okay, so now we got to fill in everything else on the ring. So it looks like the new bond is between 6 and 1, and on 1 there was this extra methyl group. Okay, so that's right there. And then it says also on 2 we had a methyl group as well, but we also took electrons away. So that means there's an electron deficiency there. Okay, was everybody good with that structure so far?
Can you go through it a little more slowly on how you knew which, I guess,
things go around the ring, basically?
Yeah, I always get confused on which ones to put the new methyl groups or whatever on.
Okay, cool. Yeah, I can definitely do that. Yeah. So this is definitely like one of the most challenging things, is like seeing a ring and being able to like draw the structure from a ring expansion. So what I would do is this. Obviously, I numbered it arbitrarily this way. Like I knew that this 6 carbon, you remember in between 6 and 2, that electron, those electrons that are in that bond are now going to be between 6 and 1. Okay, so I knew that 1, 2, 3, 4, 5, and 6 were going to be part of my ring. So I literally just drew a hexagon and wrote 1, 2, 3, 4, 5, 6 in it. That's it. Okay, I knew I took electrons away from the 2 carbon. Okay, so you can already see on the 2 carbon there's a methyl group. That's why I have a methyl group right here. Okay, so on the 2 there was a methyl, which is this guy. Let me bring another color. So it was this one. Is right here. And remember, I'm taking electrons away from 2 and putting them on 1. That's the bond between 6 and 1. That's this. So these electrons are now here. Okay, and then this 1 position, which is now part of the ring where my pen is, also had that methyl group on it. Okay, so maybe that should be enough information to get me to this structure. Okay, I think I saw another. Is that better?
Yeah.
Okay. Cool. And Farah, why does this 2-3 bond not break? Why does the 2-3 bond not break? Okay, you could have done that as well. That's totally fine. If you want to break the 2-3 bond or the 2-6 bond, whatever, you're going to get the exact same structure. Yours would just kind of rotate over to the right, but it's fine. You would still be consistent. You would still get these same stereoisomers. Yeah, good question. Okay, so we're here. So I know that was kind of hard. These ring expansions are like hard to visualize, but then we're left with just plain ethanol. Okay, so you guys can imagine now plain ethanol is going to attack at that position. Okay, so we are going to get and then we're here, and then we have one extra not one extra, but we can assume we have extra ethanol in solution to deprotonate that proton. And then, those electrons can stay, on that oxygen. So we're left with, these structures. And I'm not going to draw the major stereoisomers because, we just need to get here so far. Okay. So this is our mechanism. That's our product. So then let's kind of read these questions again and maybe, get a better understanding of what they're asking. By what they're asking, what I'm asking. All right. So for A, draw the high energy transition state at position A. Keep in mind that partial bonds are depicted as dashes. So we haven't talked about high energy transition states, but we can talk about them right now. Okay, so what the carbocations are, those are intermediates, okay? intermediates. Intermediates are at these troughs, okay, or the valleys of these reaction coordinate diagrams. So maybe if you want to write a little note in here, these troughs, B, C, and D, those are all going to be intermediates, okay? So intermediates, just some background about intermediates, they have some sort of, quantifiable lifetime where we can actually isolate that product, at a given period in time and, analyze those characteristics of that molecular structure. What a transition state is, those are at the peaks of your reaction coordinate diagram. So that would be here, here, and here. These are my transition states, and they get this double dagger kind of, it's like a T with an extra horizontal line. That's the symbol for a transition state, okay? And these have very, very, very tiny, like we're talking about like picosecond, nanosecond, order lifetime, so that you really can't isolate them. And they're thought to be like these theoretical constructs. So basically that's enough background. Let me just draw what that is. So for A, what it is, you have your starting material. Okay, so it's the beginning of your reaction, the first step. That's why I have this starting material. And what you're gonna do is any bonds that are breaking or forming are gonna be dashes. So in this first mechanistic step, let's see our arrows that we drew here. We see that this pi bond is going to break because we're gonna form a new bond with those electrons in that pi bond to hydrogen, okay? So what it is we know we're going to break this bond, okay? Form a bond to this hydrogen, and then also break that OH bond, okay? So this is how I would draw it. Okay, so this is the skeletal framework. This is like everything that isn't played with. All these bonds we're not doing any chemistry with. All these bonds on this right side of the molecule we're not touching. But remember, we're forming a new bond to hydrogen, and we're also breaking this one, okay? So do you see my dashed lines? I'm breaking this pi bond, forming a new bond to hydrogen, and also breaking that hydrogen-oxygen bond. So you just have to follow your mechanistic arrows, what you're doing, okay? And what you want to do is you want to put these brackets around it, and you want to do this double dagger symbol. That's your transition state, all right? And that's it for A. So what it is it's like this theoretical construct that, at this instantaneous point in time, we have this kind of structure that has partially broken and partially formed bonds. That's why it's a very high energy state. You can't isolate it. That's what a transition state is. Okay? Okay. I know I'm sometimes study edge if you guys use that. I don't like study edge, but if you guys use that, they have partial negative, partial positive, like, dipole moments. You're not going to be tested on that. I know sometimes that might come up in lecture. It's not important. Okay. As long as you got that, that's your answer. Okay, B. Draw the intermediates at position B, C, and D respectively. Okay, so that might be daunting, reading this without drawing out your mechanism. But what is the first isolated product? That's another way of saying intermediate. What's the first isolated product after, this transition state? Well, we drew it right here. It was this, carbocation. So this structure is what we're talking about at position B. Okay, so I'll draw B. Okay, so that's structure B at position B. Okay, and then position C, what was the other intermediate that we isolated after that? So another carbocation, so that would have been this guy. Okay, and then D, the next intermediate after some sort of other, mechanistic step, and it looks like it's the result of this, alcohol attacking in. So at D, this is the intermediate we have. Okay, and then I think that's it for B. Okay, so B, C, D. Okay, so you can see how those structures refer to B, C, and D. Okay, so now we're here. And then it says C, draw the high energy transition state at position E. Okay, so another transition state. So let's draw that. Okay, so we know that we're following this mechanistic step right here, this one right here. Okay, so let's draw that, skeletal framework. And I'll move my paper up in 1 second. Okay, so this is the structure I drew for C. So you can tell, like, if I go back up here, what happened is that this, proton-oxygen bond is being lost, okay? And it's being gained by this oxygen on this, ethanol group over here. So that should all reflect here. This proton is leaving that, ether, and it's being formed on that ethanol structure. I know I drew it kind of funky, but you can draw it anyway. And that's my next transition state, all right? And then D, draw the final products of this reaction. So that should make sense at this point. We are at the end of our reaction, so we shouldn't have any extra steps, and we shouldn't have any, fewer steps than what was predicted. So for D, when it says draw the final products of the reaction, well, we know that we have two chiral centers. Okay, so that would be here and here. Okay, so we would have to consider, the trans and the cis geometric isomers typically, but what's unique here is we don't know the identity of this chiral center. It was actually generated throughout the mechanism. Okay, you can see through this shift, this ring expansion, we generated these two chiral centers. So actually, we have a combination of 4 major stereoisomers, not just the cis trans guys. Okay. And you would do, wedge, wedge, dash, dash, wedge, dash, dash, wedge. I'm not going to draw them all out, but, I can just draw this here again and just tell you that, that's your main product, and then you can draw your 4 stereoisomers. Okay, so that was A, B, C, D. And then E, what is the rate determining step of the following reaction? So you can know absolutely nothing about organic chemistry and get your free point here. And your rate determining step, if you remember this from Gen Chem, is the rate that the mechanistic step that takes the longest amount of time to accomplish. So you can use that logic and basically say, well, the one that takes the longest time to complete is going to be the one with the highest energy barrier, or the step that requires the most energy input. Okay, so you can tell this is an endothermic reaction, clearly. And put some energy into our reactants to get higher energy products. So, it takes so much energy to complete mechanistic step A in comparison to the activation energy for, this step, and that step. So we would just say A. All right, so these reaction coordinate diagrams seem scary, but they're really not. It's just draw your full reaction out and then answer the questions accordingly. All right, any questions on this one? I would really know how to do this one. I have a feeling that this might be, a very good way to ask, mechanism questions on a multiple choice test. Obviously, in a normal semester, we would have you do this on paper and we would see all that. But, on a multiple choice online exam, I feel like, pick the structure, like from a list, like maybe like pick the structure that corresponds to A or B or C or D or E or F, and it can test all these, skills. And I think I had a question. Let's see. Chemistry. Okay, so you're getting anti confused. That's the bromination reaction, or halogenation reaction. That's the new material that we haven't talked about yet, but I'll clarify that for you in a sec. All right, and anybody else have any questions on this reaction coordinate diagram? I think we're good.
No, just to reiterate, A is the RDS because it takes the most energy.
Yeah, exactly. That's all you need to know. Yep. Anybody else? All right, cool. All right, so we talked about these alkene reactions last time. So, these were just the hydrohalogenation ones, really easy. We also talked about, these acid catalyzed hydration ones, really easy. Let's just do a quick example again. So maybe let me pick one on the other page. Okay, so let's just do, J real quick. So I see water, acid, I'm thinking hydronium. This is how fast you guys should be on your test. Okay, I'm saying, oh, pi bond nucleophile, hydrogen electrophile, boom, I'm going to follow Markovnikov's rule. That's going to put a carbocation on the tertiary position, that hydrogen on the second position. I'm left with water. Water is going to come in and attack. So then I would expect, water there. Okay, easy. That's it. So this is an achiral center because we have a sigma plane. So you would just leave that major product. All right, but that's how fast you guys should be on your test. All right, just do practice, practice, practice. You guys will get it. All right, we talked about, this ether version, and it's the same exact thing as above, except instead of, 2 hydrogens being on water, one of those hydrogens was replaced with this carbon chain. Nothing else has changed. All right, now we're going to be on our new reaction. This is called, I think we have 4, 5, and 4. I think we have 4, 5, 6, and 7 to do today. So let's just talk about those real quick. All right, so I'm going to show two different ways to do these types of reactions. So we're on reaction 4, halogenation. So now it's just adding, chlorine or bromine. So these diatomic halogens, it's only those two that you'll see. And then some sort of inert solvent. So I do my organic research typically in Dr. Summerlin's lab. So I work with a lot of these chemicals and solvents. So we actually use, this is CHCl3 is chloroform. So that's like the gas that makes you pass out. So CHCl3 is chloroform. And CHCl2 is going to be dichloromethane. That's another inert solvent. And then sometimes you'll see it as DCM, dichloromethane. So, just be able to recognize these, CHCl3s or CHCl2s or DCMs. They don't do anything in the sense of a reagent adding into your product, but they, have some extra things that they do in the reaction. Not important for your class, but just be able to recognize that, these solvents are here for the ride. They're not going to be present in your structure, but you definitely should get in the habit of writing these solvents in when you're doing reaction practice. Okay, so for the purposes of right now, I'm just going to cross these out, okay, because it's not going to react. Okay, but just know that you definitely should write some sort of inert solvent with these reactions. Okay. So this is the first reaction we're going to deal with, and it's called the concerted mechanism. So I'll write that here, concerted. And concerted is just a fancy word for, one step, a lot of things happening in one step, okay? So let me draw what I mean by that. So I have, this benzene ring. Okay, and I have this chlorine starting material. And my mechanistic steps, let me grab red. My mechanistic steps are going to be, I have another question. Oh, okay, so my mechanistic step is going to be this nucleophilic pi bond, grabbing this chlorine, okay? Then, this chlorine breaking, because, you can't exceed the amount of electrons on this chlorine. If I formed this bond to it, then it would have way more electrons. It would have 10 electrons instead of 8, so we have to break chlorine. But when you, pull this pi bond away, you're forming a chloride carbon bond, okay? You can imagine, let's just assume that it's maybe let's just say it's at that position. Let's just call it A. Maybe at A, I'm forming this new carbon-chlorine bond with that lone pair, and that would result in, partial positive carbocation center right here. So there's actually one more arrow that comes back, and that's going to form this chlorine bridge, okay? So the pi bond electrons form one bond to the chlorine, and then one of the lone pairs present on the chlorine is going to form another bond to the other carbon of that alkene starting material, okay? So you need these 3 arrows all at once. That's what concerted means. You're going to form this chloride bridge, and you're going to also generate free chloride anion. Okay? I know that was a lot of things, but I'm going to say this a couple times. Okay, so the results of that step is going to be, this structure, and I'm going to draw this 2 different ways. Actually, let me go on a separate sheet of paper for this. So I would do okay, so you could either draw this one or you can draw this one. Okay, to indicate stereochemistry. And then what we have is free chloride, hanging out. Okay, so where does free chloride like to attack? So let's think about that. Let me take this structure, okay, and let me draw 2 resonance structures with it. Okay, so here, let me fix the camera for a second. Okay, so let me draw 2 resonance structures. So let's say I did this set of mechanistic arrows. Okay, so that resulting structure for the bridge intermediate, we have to show the stereochemistry. No, I'm proving something. Just hang in there, Taylor. One sec. I'm proving something to you guys. So then we have this structure. Okay, and then let's say maybe I wanted to do these sets of mechanistic arrows. Okay, so let's classify these, positive centers. So a positive on a chlorine is extremely, extremely unstable, okay? The reason why this is so unstable is because we know how halogens are very electronegative. So the fact there's a partial deficiency on it makes this very unstable, okay? So then let's look over here. So here we have a, tertiary carbocation. So that's a really, really stable oh, tertiary benzylic, I should say. Tertiary benzylic, which is even more stable than just tertiary. And then over here is just a plain secondary. So clearly we can see why this structure is the most stable. So it should now give us some insight as to why our chloride is going to be regioselective in the sense that it's going to attack, you know, this carbon, the more substituted carbon of, you know, this halogen bridge. And the reason why it attacks that more substituted position is because we have a more stable electrophilic center. Okay, this is a very unstable center. This is a very unstable center, but this one is a pretty good electrophilic center for that chloride nucleophile to attack into. All right, so we're going to expect the mechanistic step of this chloride to attack into that more substituted position. Okay, so I'm going to draw that here. Okay, and then that bridge will break. Now, so that was a regioselective choice. Let me call that regioselective. It was regioselected in the sense that I had a choice between, you know, position 1 and position 2, and I picked position 1. However, this reaction is also stereospecific. So it's also stereospecific. And what stereospecific means is that, you know, since I have this chloride bridge, let's say on a dash orientation, that's a pretty, you know, sterically hindered face of the molecule. And the reason that is, you know, there's this atom with all these lone pairs and there's a lot of repulsions going around. So, you know, for lack of better terms, I can just say that the back face of this molecule is packed and I can't access any of those atoms. So that, in this specific structure, this one right here, that tells me that this bottom structure, the only place that I can attack is the front face or the wedge orientation. So you can imagine that this chloride anion is going to come and attack on the wedge face over here, forcing this isopropyl group onto a dash, and then this chloride is just going to move over to the right and stay as a dash. So let me just draw the result of that. I know that was a lot of words, but so remember I said the chloride has to come in on a wedge, and then this chloride has to come on a dash. Well, it turns into the dash, okay? So that would be the result of this first, you know, structure. And then over here, if I were to do the same thing, it would result in, I'm going to draw this arrow down here, and it's going to be okay. And the specific, you know, term that we're going to use here is this structure and the structure are my products. And the specific, you know, term that we're going to use to refer to the type of stereospecificity is called anti-addition. Why is it called anti-addition? Well, that's kind of self-explanatory. It's the fact that you have to add on the anti or opposite side, okay, because of the steric argument that we were talking about. Okay, so that's pretty much it for halogenation, okay? A lot of people don't like this depiction of it. Some people like to do this. So if you just, this is another alternative to drawing these reactions. So let's say I have that same starting material. Okay, so I have this starting material. What you could do is take it, rotate it 90 degrees, and then draw everything like as this planar natta projection. So essentially what that would look like is all I'm doing is rotating, just say 90 degrees, and the resulting structure is going to be, you know, this pi bond with this benzene ring coming out, okay? That isopropyl group going in, and this methyl group going out, and that hydrogen going in, okay? Do you guys see that? All I did was take this molecule with my hand, and I rotated it like this, and that's what we see, okay? So then when you're drawing this chlorine bridge, some people like to draw this, the bridge, as a planar depiction. This is typically what I do, honestly, but I know not everybody likes this. Okay? And then you can clearly see, oh, okay, like if I'm attacked, like you don't have to worry. The reason why people do this one is you don't technically have to worry about the anti-addition, like in terms of the wedge dashes and making sure that, you know, they're the right configuration, because you can already see right here that this is the more substituted side. So the result is going to be this. Okay, so that would be the structure. Okay, so it is totally valid, but notice how all we did was we changed, you know, what was in wedge, what was in dash, and what was in plane from this structure to that structure. Okay, this is also valid. The reason why people like this one better is because you don't have to worry about the anti-addition with respect to the chlorines because they're in plane. But to prove that they are anti-addition, let's just draw a quick Newman projection, and you can see that we have chloride, pH, that one. Okay, and you can definitely confirm that those chlorides were added anti-addition because this is the well, not anti-conformer, but you can tell that those groups are anti to one another. Okay, I don't know. Pick your poison. Either one works. Okay, cool. So that's that one. So let's just draw, maybe let's just do Q real quick. So this is going to be like a fast predict the product. So what I would draw as a nice intermediate would be, maybe this group like this. Okay, so, there is also the alternative structure where we have the dashes, so keep that one in mind. Okay, so then if the bromine is going to attack the more substituted side, that's definitely going to be this position. And if it attacks, let's say, if this is the wedge one, it has to come in on the dash phase. So, my two structures are going to be, maybe a dashed bromine here, which makes that methyl group a wedge. And then this bromine is going to stay a wedge over here. Okay, that's one of them. And then the other structure is going to be, if we did the dash one, it would have to come in on a wedge. Okay, a wedge bromine, forcing that methyl group to be a dash. And then we said that this one stays the way that was the original. All right, and that's how you draw these two pretty quickly. All right, I think that's enough on halogenation. Does anybody else have any questions on these? All right, so let's move on to halohydrin synthesis, okay? So the only difference between reaction 4, which was forming these, bromine bridges or chlorine bridges and having these anti-addition halides add onto these carbon chains, is that we replace this inert solvent for a reactive solvent, okay? So inert basically means doesn't react, so that makes sense why I crossed out dichloromethane or chloroform. But here, water is gonna actually react as well. Okay, so in terms of mechanism, it's the exact same series of steps as before, okay, but we just have a different type of nucleophile reacting in step 2. Okay, so let me draw you for a second. So for you, we have this. And how am I doing on time? We're doing good, okay. So my mechanistic step first is going to be, these arrows. Make sure that they all make sense. I think I gave a good rationale for that. And then the resulting structure is going to be, let's just say for, purposes right now, let's draw, this wedge one, this wedge bridge. So let's say the bromine approached on, the wedge orientation. And I'll also draw the other one just so that this visually makes sense to you guys. Okay, so those would be the two possible intermediates. This bromine can either attack from the front face, okay, and if you can't rationalize that, remember these pi bonds result from unhybridized p orbitals, so you can imagine, these p orbitals, and I could have either attacked from, this top face, which I'll draw, maybe I'll color in blue, that's the top, and that would be this wedge orientation, so that would be this structure, or maybe the bottom lobes, which would be, resulting in that structure. Okay, so maybe that visual makes more sense now. Okay, we talked about this argument before. It's regioselective in the sense that we want to attack the more stable electrophile, and the more stable electrophile, once you draw these alternative resonance structures, is proven to be at the more substituted position for reasons we've talked about, hyperconjugation, we know that. Okay, so that means that the bromide anion, like we saw above, is going to attack at that more stable position, but that's not what's actually going to happen here. What's going to happen here is the water is going to act as a nucleophile and attack at the more stable position. The reason why water, so you do have bromide in solution, and you also have water in solution. The reason why water is going to attack more so than bromide is because water is a better nucleophile than bromide is. Bromide is extremely electronegative. It does not want to give off its electrons, as much as an oxygen would. So that's why oxygen wants to fix that sufficiency more so than the bromide would. Okay, so that all these arguments should kind of make more sense. So then, we can imagine that that water molecule is going to attack the more substitute position of that bromine bridge, and then this bond breaks. Same thing going on over here. I'm just going to draw another water situation, and that's going to attack this side and that side. Okay, so the resulting structure, and I'm going to skip the deprotonation step. I think you can see that there's going to be a deprotonation step, but essentially you would result in, this. Okay, so again, these would be my two products, okay? Notice that this is anti-addition yet again, so it's again another regioselective, and stereospecific. Okay, and this is called a halohydrin because we have a halo, which is stands for halogen, and hydrin, hydrate, so some sort of water adding in, so halohydrin. Okay, this reaction is going to come back in chapter 11. Okay, so this one specifically you'll see again in Orgo 1. Okay, so make sure you guys know how to make halohydrins. Okay, and that's that one. So basically, these two reactions, although they look different, are pretty much the same thing. Just you're forming a halohydrin when water is present, and you're forming just this vicinal or this di-substituted halide when you have an inert solvent. Okay, any questions on halogenation or halohydrin synthesis of alkenes? Dope. Okay. We're gonna keep moving, and I think we have 2 more reactions to cover. All right, so let's just talk about why for a quick second. Right. So this is a very common thing that TRIP students have every semester. Intermolecular reactions, okay? So there, and I think Dr. Peterson released a 7-minute video today on Canvas supplement referring to these reactions. That should be a hint as to how important these are. So definitely, get a good foundation for that as soon as you can. So what Y is essentially we have some sort of reagent. And when this reagent reacts with this molecule, we can see, maybe a different functional group, maybe this alcohol, potentially acting like water and attacking a chloride bridge and forming a halohydrin. It's possible, and it actually is going to happen in this example. So if you had no idea what I just said, I'm going to prove it right now. So for Y, I'm going to rewrite on this separate sheet of paper. Okay, I'm going to do it right here. So, right now alone, if I were to just show you this product, in solution, you would say that it doesn't react with itself, and this is exactly what we're going to have in a beaker. Okay, nothing happens. But the minute I subject, chlorine to this reaction, okay, then, and maybe I should have put, some sort of solvent. Actually, no, I should not have. I'll leave that for now. Okay, and what's going to happen here is we're going to form that same halogen bridge. Okay, so let me draw actually the chlorine out so you can see that mechanistic step. Okay, so we have this chloride bridge. So the result of that step is going to be maybe this chloride bridge on a wedge, or maybe this chloride bridge on a dash, okay? But we don't have water in this situation as a separate reagent because water, in quotes, is technically already present as a functional group in the molecule. So who's to say that this water molecule or this alcohol functional group can't just attack at the more substituted position and close the ring? Okay, so let's number the constituents of this ring. So that would be 1, 2, 3, 4, 5, 6. Okay, so we have a 6-membered ring with oxygen being one of them. Again, same thing over here. So we would say oxygen was 1, 2, 3, 4, 5, 6. Same thing, 1, 2, 3, 4, 5, 6. Okay, so on position 6, you're going to have this group chlorine, group chlorine. Okay, and you could have either attacked from either position. So let's think about that. If I was going to, maybe attack from the back face, that would form maybe a dash. And then if I were to attack from the front face, that would have formed the wedge version. Or you could have just realized that you generated a chiral center and you have to make sure that you draw both major stereoisomers. Okay, so that's the result of this step, of this reaction. Interesting. Okay, so definitely keep in mind these intermolecular ring closings. Okay, it's common. And we'll see some other examples of those throughout the semester. All right, we're going to talk about oxymercuration and hydroboration real quick. So honestly, oxymercuration is a complete waste of time. The only time you will be tested on oxymercuration is this one exam, and it will never come up again, because you guys can tell that, if you guys have already gone over this stuff, oxymercuration is going to lead to the exact same product as acid catalyzed hydration. What I mean by that is, if I were going to do, maybe these sets of conditions, or I were to do maybe these sets of reaction conditions, you would get the same product. Okay? And this reaction is way easier to explain in terms of mechanism at the introductory or orgo level than to explain the complete mechanism of this oxymercuration reaction. Okay, so you guys are going to be able to, in the future, just go, say like, oh, I need to make an alcohol somehow. You're not going to pick this one. I mean, you can, and you'll still get full credit, but why would you write this full thing out? This one, there's so many different things to remember, 2 separate steps, all these letters, all these things, not important. The best part of orgo is you can pick and choose and use your own logic. And if you guys know that water and acid are going to form that alcohol, just commit this one to memory. Don't commit this one to memory, except for this test, because you will be tested on this one. In the future, this one won't come up again. All right, anyway, so let's just see what's going on in Z. Okay, so Z. Okay, so oxymercuration. So we have this weird, reagent, and it's like mercuric acetate is the name of the reagent, and it forms this cyclic osmate, not cyclic osmate, excuse me, that's a different reaction. It forms this like cyclic mercuric acetate like bridge, just like we saw with like halogenation, okay? So essentially what I'm going to do is I'm going to draw this. HgOAc, HgOAc. So that's another way of writing mercuric acetate, okay? Mercuric acetate. And it's that same concerted step. So, we have this, group going here, displacing that, and then also coming back at the same time, okay? So you're going to form this like mercuric, like acetate, like cyclic bridge, just like we saw with, that halogenation reaction. So you guys can expect, let me just draw the one on the wedge face, just as an example, HgOAc positive, and that methyl group is on a dash. Okay, and there's also the plus, let me just write plus enantiomer so you guys know. Okay, and that's all you guys know so far in terms of this mechanism. All right, then water is going to be my next. THF is a solvent I also come to contact with in orgo, my orgo lab, and THF stands for tetrahydrofuran. It's another inert solvent. So for your purposes, it's not going to do anything. Okay, so another inert solvent. So far we have, chloroform or DCM and THF. Those are all inert solvents. So if you ever see those in these reagents, you can ignore them in terms of your major stereoisomers. Okay, so clearly we have the same thing where water is going to attack the more substituted position for reasons we've talked about ad nauseum at this point. And water is going to attack the more substituted position to form an alcohol. So I'm going to go right to that product and not show that, because I can assume you guys know where water is going to attack and that deprotonation step that happens after. And you guys are going to be left with, maybe this, HgOAc. And, we'd attack from the back face. So that would form an alcohol on the dash there. And, the wedge here. All right, so we're here. Then, that's all you need to know in terms of your mechanism. If we were to ask you any sort of mechanism questions on your test, it's just being able to do this cyclic, concerted mechanistic step, or showing that water adds in. Sometimes we ask you to like draw this instead of drawing the product, like draw the cyclic mercuric acetate intermediate, and that would be this guy. If we say draw the products of step 1, that would be this guy. If we were to say draw the products of step 2, we don't need to, you're not taught the mechanism, so you don't need to know this. This will be an orgo 2 thing, but it basically just removes that entire HgOAc group. So you can basically say, oh, this product of step 2 is going to get rid of that whole guy. We don't need to know how it does that, but it does. And we're going to be left with, these sets of geometric isomers. Okay, so we have this, looks like trans conformer, and then we also have the cis one where that chiral center changes. So I would just put a star here to know that you have to draw the other chiral center of that configuration. Okay, so that's it. So you can tell, let's say I treated the same starting material with water and acid, and I would have just predicted that an alcohol would have formed here anyway. And you can tell it's the exact same thing, okay? But just with different reagents, okay? So yeah, that's all I would really know for oxymercuration, but there's something I want to talk about in AA. Okay, so in reaction AA, you know, we can imagine that you're going to, you know, form an alcohol on the more substituted position. Okay, so I see that I have this primary position over here, or I have this tertiary position right here. Clearly, I'm going to form this tertiary position, you know, clearly I'm going to form, you know, something at that tertiary position. However, what a lot of people get confused is that nowhere in this mechanism did I ever talk about carbocations. I never talked about carbocations, which means no rearrangements are going to form. So a lot of the people, you know, in your class are going to say like, oh, I see this, you know, telltale sign of, you know, this 4-membered ring with this pi bond outside. I'm going to predict that there's a carbocation, do a ring expansion, all those things. But that actually does not happen in this situation because we're never going through a carbocation ever. So in this situation, we are not going to rearrange. So what happens is you're going to have that same starting material, but you're still going to be rejuice selective, but there's just going to be no rearrangements. We're still going to prefer that tertiary position, but we're not going to rearrange because, you know, we never went through a carbocation. So definitely like keep that in mind. You have to know all of these key mechanistic steps. I think I said that. Lack, and I said it right here, the lack of carbocation intermediate throughout its mechanism, meaning that you cannot rearrange. Rearrangements are not possible, okay? I think I have some questions going on. Let's see. D is not, okay, Z is not a chiral, Samantha. And I think Hannah answered that, yeah. So it is not, even though you can technically draw a sigma plane through the center of the ring, whenever you have di-substituted, meaning like on 2 different carbons, you have substituents, di-substituted rings, you have these geometric isomers that exist. And even though, you know, you may not have, you know, chirality in the sense of, you know, these R and S, like diastereomer and enantiomers, you can still have chirality in the sense of geometric isomers. Okay, so geometric isomers are still chiral, and you need to draw those main stereoisomers as according. So the trans isomer is going to be the ones where the largest groups, so, and clearly on this carbon, it's the tert-butyl group, and on this one, it's going to be, the highest priority is going to be the alcohol group. So those 2 groups in the trans arrangement are going to be opposite to one another. So this tert-butyl group and that hydrox group are opposite. Wedge dash, that's trans. If I were going to draw the cis conformer, it would be, you never touched the stereo, you never played with the chemistry of that tert-butyl group, so leave it as a wedge. But the cis one is going to be where that hydrox group is also on the same face as that tert-butyl group. And that methyl group is now on a dash, so that would be cis. Okay, so hopefully that made more sense, Sam. And thank you, Hannah, for helping her out. So if you couldn't see that, that was that. Okay, and then finally, let's do hydroboration oxidation, and that's what we'll stop for the day. So let's go to EE. So for EE, we have these reagents that we haven't seen before. Okay, so everything up until this point has followed something called the rejuice selectivity rule or the Markov-Nikov rule. Okay, so that basically means that we're going to form alcohols on the more stable or more substituted position. However, with hydroboration, oxidation, we're actually going to see the opposite. We're going to see the addition of an alcohol on the opposite position, okay? So what we can basically imagine is, why is this BH3 being used? So THF, again, remember we talked about inert solvent, inert solvent, inert, 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 so we're not going to really worry about that. But what is BH3 going to do? So let me grab another sheet of paper, and I'm going to try this out for you guys. Okay, so this is really interesting. So this was discovered, I think, in the 1900s, like early 1900s, when scientists like discovered that BH3 like has this really cool property. And what it is I'm going to draw this transition state for you, even though this is not what the question's asking. But the BH2 fragment this is really important, this structure. Okay, so make sure you guys can recognize and draw these intermediates. And what it's basically saying here is that this borane is actually one of the exceptions to the octet rule, okay? in the sense that it's allowed to be electron deficient. So there's only 6 valence electrons here. And it's trigonal planar as such. Remember, we have 3, areas of electron density. That's calling me sp2. That's trigonal planar, all these things that we know, trigonal planar. However, what you can kind of see here is that we have one region of the molecule that looks more sterically hindered than the other. And if you were to draw a line through this boron, you can see that this side, we can say, is more sterically hindered. So sterically hindered. And we can say this one, maybe by proxy is sterically unhindered. And you might be asking yourself, like, how do I know it's sterically hindered and unhindered? Well, literally 2 hydrogens and 1 hydrogen. That's all the logic I'm using. Okay, so if we're doing a steric argument here, would it make more sense for this BH2 side to align with, the more substituted, more, electronically crowded side? Or would it want to align on the less electronically clouded, the more sterically accessible side? And if you said more sterically accessible side, you're totally right. And that's what I'm proving right here, is that this BH2 side is going to align regioselectively to the less substituted side of this pi bond, because that just makes sense. If this is a big bulky group in comparison to this singular hydrogen, then the BH2 group is definitely going to want to go on the less crowded side, and that's what we're showing here. And then this H group, this H fragment from borane, is going to add to the more substituted side. So really the steps of this reaction, or of this transition state, is going to lead to a structure that looks like this. Okay, so you have those bonds formed, okay? And then we don't know the mechanism for step 2, but you guys can just rationalize that sodium hydroxide is a source of hydroxide. So it's a source of Na plus and OH minus. And you guys don't need to know what hydrogen peroxide does either in this mechanism, but just realize that that OH is really just going to remove this group and replace it with OH. Okay, so notice that what you did is if I were to take this reaction and substitute it to oxymercuration conditions, which follows Markovnikov's rule, that would have formed an alcohol here. Okay, an alcohol here. That would have been Markovnikov. But that's not what we observed. You can clearly see that the product down here has the alcohol on the exact opposite of what we wanted. So this is the anti-Markovnikov way of adding alcohols into alkenes. Okay, so if you want to predict the products real quickly, I see I have a primary position and a secondary position. We know that this is clearly going to be hydroboration oxidation conditions. So I'm thinking anti-Markovnikov alcohol, which basically means less substituted alcohol. And then I would just go right to the product like that. It's that quick. All right, and again, no carbocations, which means no rearrangements. But something I want to talk about is, yes, this is regioselective in the sense of how this borane aligns, but it's also syn-addition, okay, or stereospecific in the sense that it's syn-addition. So we know what anti-addition is. We saw that. Anti-addition is with, that bromine bridge, that, mercuric acetate bridge, and the halohydrin bridge, all those things. That was anti-addition. But this is the first example that we're going to see of syn-addition, okay? And syn-addition. Why is it syn? So syn means same phase. And it's syn-addition because we see, this borane is one molecule. And it's pretty tiny, honestly. And if, this molecule is going to approach, maybe the front face of these, maybe the front face, let's say it's the front face. That BH3 group, that whole BH3 molecule is going to approach together. So whether or not, it's we need to know where the BH2 side's going to go and the H side's going to go. It doesn't matter, but we know that at the end of the day, both of these fragments are going to come on the same configuration, the same wedges or the same dashes, because, they're so close together anyway. So, a way that I can depict that is this. Or, okay, so it's syn-addition with respect to, the borane atom. Okay, that's what we're talking about, syn-addition here. So yeah, you would say that this is regioselective and stereospecific. Okay. And I think that's good right there. You guys haven't done ozonolysis, but let me go real quick and we'll wrap up with page 71. Okay, so how much time do I have? I'm basically out of time, but I want to just do this real quick for you guys. So 71, I compiled these questions because these have been tested in the sense of they've been discrete questions, like, most missed, honestly, because people don't think to know these things. So I compile them into like this one page. So these are kind of like miscellaneous things that I've seen asked in my semesters here, TA. So for one, draw just the cyclic osmate intermediate. You don't know that yet, but just drawing this plain intermediate is all we want. Okay, so it wasn't drawing the mechanism, it wasn't drawing the product, it was drawing a specific intermediate. Okay, so you can kind of see how that applies to today. For B, you know how I keep saying stereospecific, regioselective, all of these things, you need to sometimes be able to classify them. So, here I purposely omitted that stereochemistry because I want you guys to be able to know, for reactions A, B, and D, A, C, and D, you don't know B yet, but for reactions A, C, and D, how are those reagents adding? So let's talk about that. For A, we know there's going to be a regioselective argument because we know that water is attacking one specific region in that mechanism. It was attacking that, more substituted side. And more specifically, we know it's also going to be stereospecific because we said that, whatever face that chlorine is on, let's say that chlorine bridge is a wedge, that oxygen is going to have to attack from the opposite face, which is the dash, and that's gonna result in these anti-addition groups. So it's both regioselective and stereospecific for that reason. You just have to use that logic. So that's B for both. And then for C, we talked about the regioselective argument where the BH2 group is going to add to the less sterically hindered side. The H is going to add to the less sterically hindered side. But we also said that one thing about syn addition. It may not seem like syn addition because we don't see the two groups in the end product, but it is syn addition with the borane fragments. So again, this one is also both. And then for this one, are we stereospecific for D? We definitely know we're regioselective in the sense that we follow Markovnikov's rule. That's why we have this secondary ether, not a primary ether. So we know it's regioselective, but is it stereospecific? And no, it's definitely not stereospecific because we said we would have, that unhybridized p orbital at that carbocation, and we can attack that front or back face. So this is just regioselective, not both. And then for C, we did talk about this, draw that relevant transition state of this borane fragment. Okay, and I'm gonna leave that for you guys to do at home. And for D, we also talked about that. Draw that cyclic mercuric acetate intermediate resulting from, just that one step, that one concerted step. So again, these are some discrete questions that, trip people up. I will do D for you right now because D is confusing, and then I'll let you guys go. So this is a situation where I would actually rotate this in plane. So pick it up, rotate it like that. And the reason that I do that is because there are so many carbons that are attached here. So I'd want to draw that. And I would draw this propyl group. So I'm not going to draw PR for propyl, and I'm going to draw this isopropyl group, and I'm going to draw that methyl group. So all I did was take this and rotate it like that. So your mercuric acetate bridge can either approach from the top base. Remember, we have this. No, I'm just going to draw these p orbitals. You can either attach from the front base or the back base. So let's say I attach from the front base. So that's going to result in a structure that looks like this. Okay, or I could have attacked from the bottom base, and that would have resulted in a structure that looks like this. And the exact same stereochemistry applies. Okay, so that's why people like to do it. That's why I showed you my way of rotating it, because you don't have to deal with the stereochemistry of the bridge. You can just, keep the stereochemistry of your substituents the way that they are, and then just draw the approach of the mercuric acetate reagent, from the top base or the bottom base. Okay. So you guys can tell we're definitely getting more complex here in Orgo, but nothing too crazy. If you haven't already done so, watch my chapter 6 review video on alkane reactions, because that's going to help solidify everything together. And I'll see you guys on Wednesday to wrap up the rest of the chapter 6 material. And I think on Friday we'll begin chapter 7, okay, which is alkynes. All right, so keep this going. You guys got it. And I will post this on YouTube, and I will see you guys on Wednesday. Good luck.
Hey, can I share my screen real quick for a homework problem?
Yeah, of course.
Okay, cool. It says I can't share it.